Okay, today the reading assignment 3 is due, and we're going to look at some programming problems that that we can use to try to understand some of the learning objectives that there are for this particular reading assignment. We have something called the Boolean data type, conditional expressions, comparison expressions, and loops, and nested branches, nested loops. So we're going to look at these issues today and perhaps Wednesday as well. And so the way I want to tackle that is just to dive into Lab 3. So Lab 3, the first group of people will go today, and then the second group on Wednesday. If you're working in the lab, if you're working at home, of course you don't have that schedule. So let's take a look. And today, I think what I'm going to do today is use Visual Studio and work in that environment. So I'll illustrate how to use that to do the problems. So I think I'll just leave that. And all right, let's do that. Actually, I should show you how to manage the repository. So let me just take care of that quickly here. So I'm going to look here. Wait a minute. Oh, there it is up there. So here's the URL for the repository. What's that? Oh no, I have it right here. It's all set. All right, so just pasted it from the website. You can all, and the procedure I'm carrying out right now, you can also carry out. If you want to make a copy of your work into a new folder or onto a different machine, you can do that easily. Okay, so what I'm going to do here is start Visual Studio. Just like these folders that we have for these assignments in the labs, I'm going to create a folder for each problem that I work on. I'll create a solution. There's two ways of doing this, actually. We can create a single Visual Studio solution and put all of our project folders in there. Or else we can, where each Visual Studio project in the solution would correspond to an assignment or a lab exercise. And so what I'm going to do is use the strategy that each exercise, each programming problem that we work on has its own Visual Studio solution and Visual Studio project inside of that. So let me show you what I mean by that. So we're going to create a new project. It'll be a console application. And we're going to call it Lab 031. That's the first problem, first exercise in Lab 3. And I'm not going to create a directory for the solution. By default, that's when you start up Visual Studio, that's selected. But I'm going to uncheck that. And let's see what happens there. I like to start from an empty project. I think it's simpler. And it's easier to create code that is portable between Windows and other operating systems when you select empty project. I don't use, these are virtual folders. I don't use these. And let's go ahead and add a new item. Let's add a main.cpp. Let's write a program that says hi, just to see if we have everything configured that we need, configured to write and run a simple program. So we're going to add a new item. It's a C++ file, and the name will be main. There it is. Let's go ahead and take some existing code and paste that in there. And let's build the solution. Down here is the status of the build. Build 1 succeeded. Let's try to run it. This is one way to launch the program in what's called debug mode. There it is. Now the window, because I have this command C and get, it's waiting for a keystroke. If we didn't have C and get there, we wouldn't pause and wait for a keystroke. Let me show you the difference. Oh, by the way, I just clicked run. I made a change and I clicked to run. Oh, but we didn't give the compiler a chance to compile the code into an executable. So it's Visual Studio is giving them the message that the project is out of date. It hasn't been built since the last modification. Would you like to build it? Yes. As you can see, the console window appears, buy is printed, and then the console window closes right away. And one way to get around that is just to read a keystroke. Another way to get around it is to set a breakpoint. Let's try that. I just clicked in that margin there. It's a little red dot. That's called a breakpoint. So execution is going to pause there and wait for us to give what's called the debugger. The execution is going to pause. It's going to wait for us to give a command to the debugger. As you can see, there's a little yellow arrow inside the red dot now. It's because you can have many red dots. We can break in more than one place. We can set them anytime we like. And the console window's in the background here, so I'm just going to bring it forward. And that's it. So we're pausing here. Execution is in a hold and wait state. Now we have some options up here. This is step into, this is step over, and this is step out. And what I'm going to do is also there's a hotkey F10. I can press F10. Step over means just execute wherever you are and continue on one step. The other option, so these are three different, and I'm not going to explain those right now, actually, all three of those, but that's one of the choices that we have, one of those three. The other choice is to resume. So you can see the hotkey there is F5, and the tooltip says continue. So we can just press that to continue. It just terminates, because we return from main at this point. That's the debugger. And the debugger, by the way, is very handy for debugging programs. Actually, if you learn to use Visual Studio, you're going to work more quickly and efficiently on the problems in this class. But it takes some time to understand how to use this tool, Visual Studio. This is called an integrated development environment. People say IDE for short. IDE, Integrated Development Environment. This is one of several IDEs that are available. This is a very popular one. This is pretty standard. And it only runs in Windows. There's IDEs that run on Linux. And there's an IDE, the most popular IDE for Macintosh is called Xcode. So Visual Studio does not run in Macintosh. To use an IDE in Macintosh, you should use Xcode or an alternative if you want that. And I think it's hard to do development on the Macintosh without Xcode. Like when you want to do iPhone development or iPad development, all the libraries that you need and the facilities that you need to write code and build it and run it on those devices, that's all packaged and part of Xcode. That becomes a very important IDE when you do Macintosh development. Okay. Well, once again, this is optional. You don't have to do this. You can continue writing code, building, and running in the way that we have been doing so far. All right, let's go back to Lab 3, Exercise 1, and see what that's all about. Practice with mathematical expressions. Write a console program that prompts the user for 3 double precision floating point values, x, y, and z. Have the program compute and display the following calculations: the sum of x, y, and z, the sine of x, the cosine of x plus y divided by z, the average of x, y, and z. So let's go ahead and do that. And let's do it a step at a time. Write a console program. Well, we did that. We have a console program. We have a shell. It's ready to go. It says buy. So that little piece is done. That prompts the user. Should prompt the user for 3 double precision floating point values x, y, and z. So let's do that part. How about if we do this? We'll do x equals and then we'll read a value called x, and we need to declare that value. That's an integer. Oh, sorry, it's a, what did I call it again? A double precision floating point value. A double precision floating point value. And we can declare that with the word double in the C++ language. The alternative to double is called float. So we could have declared it like this. But that's not double precision, that's single precision. Single precision floating point number, float, is the computer uses 4 bytes to represent that number. So some of those bytes, or some of the bits inside that byte, are used for what's called the mantissa, and the other bits within that byte are used for an exponent, for the exponent. So you have a mantissa, you've got an exponent, and you also have sign. Is it negative or is it positive? So those 3 pieces of information which are needed to specify a floating point number, a sign, mantissa, and the exponent, are packed into 4 bytes for a float. For a double, all that information is represented using 8 bytes. And you know, if you're working with financial information, like bank account balances, things like that, bank transactions, a float is not good enough, because if you do a lot of calculations, there will be noticeable rounding, so you'll lose a penny here and there, depending on what you do. And so most people, by default, programmers use a double. And float is useful only when you have a lot of information, and the storage is then, and the storage size, the storage capacity, then becomes an issue. So let's suppose you have a video game, and you have data for a video game. And the data for a video game is comprised of many coordinate positions in a virtual world space. And so you've got these huge files with coordinate information, like 3D models. You know, it's all lots of information about coordinate positions of points and normal vectors and color values. Lots of information is in there. So you can get away with a float because if you lose a little bit of precision, it's not a big deal in that situation. And a float takes half as much space as a double. So when you look at video game development in particular, you'll see that programmers work with floats, almost always work with floats. And occasionally you'll see a double, but it's not a double that's used to store a lot of information. Okay, so we're going to use a double. And so what we do is we declare the value here. We're telling the compiler to, hey, when you translate this statement into machine language to get ready to run on the computer, that here we want to allocate 8 bytes of storage data in the computer, and we're going to store a floating point value in those 8 bytes. And in the source code that we're writing right now, we want to refer to that 8-byte storage chunk with the label X. So X is like a label, like a name, and it refers to a chunk of storage in the computer in RAM. The program is running in RAM. It's not running in the disk, unless you're running out of memory and you're creating virtual RAM on the disk drive. That's a special case. We'll put that aside. So we're telling the compiler to generate machine instructions that allocates 8 bytes to store a double precision floating point value, signed value, in an area. We're going to refer to that as X. The next statement is to prompt the user. So we could say, please enter the value for X. We could write that. I'm just going to write X equals. And then the third statement is an input operation. So we have 3 symbols here. This looks like 2 symbols, but that's really 1 symbol. Okay? It's 2 greater than symbols put together, and that's considered a single operation, and that's called an input operator. The input operator has 2 arguments. It has an argument on its left-hand side and an argument on the right-hand side. And what that operator does is it goes to the standard input stream, which is some pipe of information. It's some pipe in the system that lets information flow into the running instance of the program. And we can assign different things to that incoming pipe, that input stream. It could be a file, it could be but by default it's the keyboard. So we're going to the machine instructions that get generated by the compiler to implement this statement. Those machine instructions will make a call into the operating system to pull in bytes from the standard input stream. Whatever standard input stream is assigned to this running instance. What's that called? Process. I was looking for the word process. When the program is turned into a process, when an instance of the program is created in RAM and run, that it's assigned or associated with some input stream called the standard input stream by the operating system. The program doesn't know. I don't know if I'm reading from the keyboard or if I'm reading from a file or if I'm reading from a socket, or wherever the information is coming from, I don't know. That's the operating system did that for us. So we read that in, and I'm going to come back to this expression in a moment and explain why this is. This is, in fact, a function invocation, and the function takes 2 arguments. And I'll show an alternative form of that in just a moment. So we read in a value here. It's called a blocking call. We have to wait until the user completes some input operation. And then the next line, we print a new line character, and that's it. Although we pause for a keystroke. Let's go ahead and build that and run it. X equals 8. Oh, what happened? Oh, I know what happened. That this operation left the new line character in the input buffer, and cnget pulled that new line character from the input buffer. So cnget returned right away. And this is inconvenient to do this, and it's hard to understand, but that's the nature of the beast here. We actually have to put 2 of these in there. Want to build it, check for errors, it succeeded. X equals 8, enter, there it is. So once again, it's a little tricky. When the user types this in, I type an 8, and then I type enter. And 8 is a byte value. We read a byte value from the standard input stream. And then when this input operator sees the new line character on the standard input stream, it says, wait a minute, I'm going to leave it in the input stream. It's something called a buffer. We'll leave it in the buffer. I'm not going to pull it out. I've got all the digits I need to form a number, an 8. And so when we get to this point, cnget reads that new line character from the input stream buffer. And then we pause here. We break. We block here for another key press. All right. Let me explain. I'm going to show you an alternative form for this input operation right here. It looks like this. I think it looks like that. Maybe I didn't get that. Operator. Maybe that's not defined. CNX. Say it again?
There isn't a space after operator.
Like this? Wait a minute. Why is this not happening? Maybe it looks like this. It'll take that. So operator is a function that we invoke on the object represented by cin. Let's see if that works. Oops. Right, one more time. 8, enter, enter. So this is another form of this input operation. So it looks more like a function call now. It's calling a function on an object, which we didn't cover yet. And apparently there is there's no global function for the input operator that takes cin as the first argument and and a double is the second argument. All right, so I'm gonna switch back to the familiar form. So we need to get x, y, and z. So let's read those in. That's x, this is y, this is z. I'll get rid of this. So we declare the three variables, we allocate storage for them, we input the x variable after prompting the user, we input the y variable. Oh, look at that. I'm cleaning the code and I noticed a bug. There we go. Then we input the z variable here. Let's test that. Once again, we're doing this incrementally. We're solving the problem incrementally. X is 34, y is 12, and z is minus 9.4. Okay. So we've done this part of the exercise. We have a console program that prompts the user for three double precision floating point values, x, y, and z. Now let's continue. Let's do the next part. Have it compute and display the following calculations. The sum of x, y, and z. Let's take a look at that one. I'm not going to copy that. X plus y plus z equals, and then we're going to print x plus y plus z. Let's test that. So the x is 3, 4, that's 7, and then 1 is 8. There we go, we got it. So this is a mathematical expression, and I'm going to show you how to read this line right there. There are three operators in that statement. A statement ends with a semicolon. There's a statement there, it has three operators. How come it didn't just print x and then add y and z together? You know, why did it do it in the, why did it add x, y, and z and then send the result into cout? Why didn't it send x into cout and print that and then do something, then do the rest of it? Well, it's because the compiler is following rules called precedence rules. And precedence rules are about what operators are more important. What operators are evaluated first before other operators. So the output operator here has lower precedence than the addition operator there. So that means the addition operator will be evaluated first, executed first, before the output operator. Essentially, we could be explicit about it in our, when we write the program, because maybe we don't remember what the precedence rules are, and even if we could, well, we're just going to make a habit of being explicit anyway. Let's go ahead and put parentheses around that expression x plus y plus c to tell the compiler to do that first and then do the output operation. Because this is what's being done by default, right? I mean, we could reverse it. We could say, oh, let's try to do what, let's try to mess around here. Let's output x, and oh, well, look at that. Now I'm getting a red mark here, and we're gonna get a build error on that. See, that's one of the benefits of using an IDE, that it's doing what's called a continuous build. So I hit one keystroke here. I didn't even save the file. See the asterisk up here? I didn't even save the file. And Visual Studio is trying to build. It's analyzing the code to see if the code is buildable. It's not buildable now. It has a compilation error. And it's showing us that by having that little red underline underneath that plus sign, it's telling us that this won't build. Look at, and this asterisk means the file's not saved. So I'm going to save the file. Still there. Now we'll build it. Well, it's hard to read that. There's, look at that error message. So we're not going to take time to read that error message right now, but that's one of the skills you need to develop in this class, is how to extract information from those cryptic error messages and solve problems. So this is a build error, but what could we do? Well, see, because this thing actually evaluates. That's an expression. It's a sub-expression. This is a statement. The statement is comprised of many sub-expressions, and the sub-expressions have, you know, one is evaluated after another. And this is the first sub-expression that's evaluated, I think. It could be that this one is evaluated first, but I'm not sure. Well, actually, it can't be, but it's syntactically incorrect. So this is what this sub-expression here, all expressions and sub-expressions evaluate to something. So when I see this, I say, oh, that's something. Is that a number? Is it an object? What does that expression evaluate to? And what I mean by that is this expression, in a sense, you can think of it as being taken away, processed, and something simpler brought back in its place. And what does this thing evaluate to? What it does, this evaluates to C out. Does that make sense? That sub-expression evaluates to C out. Oh, if that sub-expression evaluates to C out, that means I can do something like this. Oh, look, no red marks. Let's see if it builds. It built. Let's see if it runs. 1, 2, 3. Oh, look at that. 1 high. See, x is being sent to C out, and x is 1. So it sends the 1 into the standard output stream, and then this sub-expression evaluates the C out. And then we send high into the standard output stream. So that's why we got 1 high. So the point I'm making there is that when you look at these statements, you have to mentally parse them. You have to be concerned with the precedence of operators. And you have to understand what operators are going to be evaluated before other operators. What is the sequence of evaluations? And the sub-expressions that appear inside the statement. What do those sub-expressions evaluate to? What is their data type? How can I use them? What is their meaning? And that's essentially a big part of what you're in the process of learning about. And this is not just particular to C++ language. This is a general issue or or subject or skill or knowledge that applies to every programming language. All right, let's return this. And let's go on. The sign of x. I'm just going to copy some code there. The sign of x. Let's put in a number that we know the answer for. What's the sign of 0? 0 or 1? I heard a 0 and a 1. 1. 1? Okay. So let's type a 0 in for x and see that it shows a 1. Oh, sorry. All right, a 0 for x. And I'm not going to worry about the other ones. Oop. Sign of x equals 0. Well, you know, we could replace x by a 0. Wouldn't that be more interesting? Let's see. Let's try that. Also, we need the this just to clean it up. We should put the new line character there so that we don't get a concatenation of those two outputs. Let's do this. Let's actually let's neaten this up. And here what's wrong with that? Why is that a mistake? How come that's an error? Missing closing quote. That looks like a bug to me. Let me save that. So, am I missing a closing quote there? I'm sorry, my ears are really bad. Can you? No, I don't get that. Let me see. This is okay, right? You know, this looks like a bug to me in Visual Studio. Let me try something. I'm going to try to clean. Look, I did a clean. It's not red anymore. See, all software is buggy. You know, I read an article this morning. Is it in CNN? Headline News, that there's a computer virus in the control systems that control the drones that the military is using in Afghanistan and other areas. And they can't get rid of it. And it's been like 3 weeks, and they're still working on getting the virus out of the drone's control system. I mean, is that crazy? So here, you know, there are bugs everywhere, and you kind of have to go with the flow here and work around things. And I knew that, well, it's what Visual Studio has here is very sophisticated. It's trying to give us information on the fly about what is valid syntax and what is invalid syntax. And sometimes it's too complicated, and it gets confused, and it's giving you the wrong feedback. And we just saw the example of that just now. So I did a clean. Clean means delete all temporary files and regenerate those cached temporary files that you're using to analyze what we're doing in real time here. So let's run that. Zero. Now sign of 0 is 0, so now it looks good. So we could do that for the other ones too. And you know, instead of x here, we would do this. We do x plus y plus z oh, that's not right. That's my error. It took that one. That was even more complicated, and it accepted that. See, what we're doing here is to understand that expression. And what is going on with that expression? Does it look like Greek? No, it looks like C++, right? But still, it could be Greek. It doesn't matter, right? So what is this? How do you mentally process that expression to know what's going on? Remember, you got to go back to sub-expressions. There is only one operator in here appearing many times. It's the output operator. And you know that these output operators appearing in this statement are going to be evaluated one after another. But which one is first? Well, it's this one that's first, because it's a left to right evaluation order. And most operators have left to right evaluation order. There's a few that have the other direction, actually. I can't remember what they are offhand, but they're there, and we'll see it when we see it. So this operator is evaluated first. And when this operator is evaluated, it takes two arguments. It takes that x there, and it takes the c out there. And when this operator is evaluated, you can think of it as being replaced by something else. It's replaced by what it is evaluated as. It has a side effect. It sends the value of x into the output stream. Okay. You call that like a side effect. But in addition to printing x, the expression, the sub-expression, is replaced by what it evaluates to. You can think of it like that. I'm just explaining it at a high level. We're not getting into the details. Well, the machine instruction, there's a an instruction pointer, and there's a register, and there's a bit here and a byte there, and we can't explain everything all at one time. So we have to make these simplifying abstractions to navigate through this the problems that we're working with. So the simplifying abstraction here is that we have a sub-expression, and it's replaced by something that it evaluates to. And what does this sub-expression evaluate to? So, huh? No. Look at what's the next operation. This sub-expression is replaced by something, and that something becomes the left-hand argument to the next output operator. So what does it have to evaluate to? See, what's happening here is this thing is being replaced by something, and that something is then used on the left-hand side of the second output operator. So what goes on the left-hand side of the output operator? Huh? No one gets it? Look, we have an output. Let me do it like this. There's the expression, and I'm going to take off the enclosing parentheses. Look, we have something. Is that going to print high? That's going to print high. So what does cout output operator x what must it evaluate to for this thing to build and run correctly? What would you replace this by? What would you replace that by to have a meaningful program or syntactically correct program that builds. Cout. It evaluates the cout. This expression evaluates the cout. That's why it's valid to appear to the left of this output operator. And what we do is, because we're relying on precedence rules and order of operation rules combined together. Actually, the precedence rules don't matter here because we only have one operator. It's the order of operation. This operator runs first. That sub-expression is replaced by cout. We say it evaluates the cout. And then that becomes an argument for the evaluation or the execution of the next output operator, so that we end up printing this plus sign. And then this whole sub-expression, and that sub-expression contains a sub-expression within it, right? That whole sub-expression also evaluates the cout. And then it's used as the leftmost argument to the next output operator, and so on. That's why we can cascade the output operator. So x is 0, y is 1, z is 1. So now we're improving the way the program runs now. All right, let's do the next one. What's the cosine of x plus y divided by z? That's a little ambiguous. Do we take the cosine of x plus y and then divide by z? Or do we take the cosine of parentheses x plus y divided by z? You know, and I don't care, actually. You could do it either way. I'd be happy, because that's ambiguous. So what's that?
It should be parentheses of x, y divided by z together.
You think so?
Yeah. I always just have some random numbers of x plus y and then divide by z.
That's how I would interpret it, too, because I think the operator plus and divided by have a higher precedence than taking the function cosine. That's how I would think. All right, so I think we can do that like that, right? So it's the cosine. Is that what I said? Cosine? X plus y over c? Oh, this is going to be too hard. X plus y over z. The cosine of that equals let's do it here. This is the cosine of x plus y over z. Wait a minute. Is this adding x plus y first and then dividing by z? Oh, it's dividing. It's taking y and dividing by z and then adding it to x. That's because division has a higher precedence. So that's what's done first. So if we want it the other way around, we're going to have to use parentheses here. Let's put that in here as well. Does that look all right? Well, it would be nice to clean that up and have replace the x by a 0, the y by a 1, and the z by a 1. Let's do that. So we use the same trick that we used before, and we're going to cascade the output operator. So wherever we see an x, we know we have to split it off. Wherever we see an x, y, or a z, we're going to have to close a string literal, use an output operator, and then open the next string literal. And we find a y. Oh, got to close the string literal, insert an output operator, another output operator, open the next string literal. It's an algorithm, and I'm a computer, and I am carrying out the algorithm right now. Oh, it shows red. Are we going to believe it? No. I don't believe it. Maybe you believe it. See, the drone control system says that it's an enemy combatant. You're going to press the attack button? Do you trust it? Okay, we got that. The average of x, y, and z. So maybe we'll skip that one, and I'll let you do that one in lab. And let's take a look at the next one. Actually, before we do that, I want to show you how to finish up. I'm going to close Visual Studio, just in case you use Visual Studio for your work. And you'll see that Subversion here is showing that this folder is new. It needs to be committed. I'm going to right-click, and I'm going to commit. And you know, it's showing a lot of stuff here. And we actually you don't need to commit all of it in there. This debug folder, that's a temporary folder that is generated on the fly as needed. So we can just delete it whenever we like. So what I'm going to do there is I'm going to right-click that, and I'm going to say add it to the ignore list. I don't want to put it in the repository. Oops, cannot do it. Let's delete it. There should be delete and add to the ignore list, but that's not there. Okay. Likewise, all of these things, these are all temporary objects. This, I believe that's a temporary object. I'm going to go ahead and delete it. And this is the solution file that's needed. That defines the solution. These are user settings, and that can be deleted, doesn't have to be. If you're working with other people, you generally want to delete the SUO file because it's user-specific settings for their system. So normally that would not go into the repository. The project, you need that. These, I think you need these, but I'm not sure. We'll leave them there. And of course, you need the main.cpp. And these all have to be selected. And by the way, you can just go ahead and commit everything. You don't have to go through this process of leaving things out, so you don't have to think about it. It's an advanced topic. You don't need to be burdened by that. Unless you want to learn how it works, you can do that. And let's suppose that I accidentally delete these. And whoops. Let's restore. I'm going to go svn update. There it is. It brought back all the files. So we've got like a backup system here. Let's see. I'm going to double click the solution file. Let's see if deleting all those temporary files was okay. And there's the the project folder. There's the main. Let's go ahead and build. To run. So if it builds, it's going to be okay. There we go. So that's that whole process. And let's go ahead and maybe do the next one. This one I think is pretty easy. Maybe the one we'll do next is this Webpage Generation program. And this starts a theme that I'm going to keep going through the rest of the quarter, which is to write programs that generate web pages. That's my compromise. I took out the graphics window programs and I replaced it with these web page generation problems. So let's see, this is exercise 3. Let's take a look at that. So it's a Win32 console application. We're over here. Let's call it Lab 033. I'm going to select empty project. It's easier. Delete these. We can create a new file, main.cpp. New item, C++ file, call it main. And let's copy our other code. So it's in here, this one. Just going to open that up. Control A, Control C. Let's close that right away. Paste it in there. Let's see if that builds and runs. This is our old code. All right. Write a program that generates a web page that contains 100 random integers. So we're going to need a loop here. The program should write something like the following into cout. So this is a HTML file. Let me show you what that looks like. For those of you who are not familiar with HTML, HTML is called a markup language for web pages. It's not really a programming language. It's more like an annotation language, or they call a markup language. So you have text and you annotate the text, and using what are called tags, HTML tags. So we see those here. And we'll show you. Let's create a file. I'll call it test.html. Let's open that with Notepad. Paste that in there. So the document or file, so we're going to create a file, and this is what the file is going to look like. It's got this HTML annotation in it because it's a web page, and then it has what's called an ordered list. OL is for ordered list, and then the list has a list items, or LI. So the first list item is 39, the second list item is 16, and so on. But we want to have 100 of these. Let's see, that's 4, that's 8, and that's 10. That's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. There's 100. But I want 100 random ones, not 100 copies of one, right? So 100, each number should be random. And whenever just double click on that, then I see the web page. So this is it's an ordered list. That's why they're numbered. And then we just see the numbers all the way up to 100. Okay, so I can right click on there and do view page source, and it shows me this is the HTML. So we're going to write a program that generates this file. And then we'll view it in the browser. Let's go ahead and do that. Let's start simple. Let's just print the HTML tag. And let's see if this builds. And that builds. And I want to show you something here. In the file system, and you go into this debug folder, and you see, there it is, lab031.exe. That's the executable that got generated. So we can run that executable. Let's do that. I'm going to copy the path to that folder where the executable is in. I'll open up a console window. I'll type in CMD down here. That's one way to do it. There's other ways. And then I'm going to CD and Control V doesn't work, but right mouse click paste does. And so we're going to CD into that folder, dir. Where is it? It's lab 03.exe. Look at all the other things, .exe, .intermediate, manifest, all this other stuff in there. So all of these are temporary files that Visual Studio generates just for it to do its work. But we're not concerned about those. So if we run this, oh, what's going on here? Am I in the wrong folder? I'm in the wrong folder. I'm in 0301. How did I get to 0301? I'm in the wrong folder. I should be in this folder, right? Oops, not 2, 3. There we go. Let's go into the debug folder. And here's the executable. Now we're running. There's the HTML right there. Well, we're not going to run it like that. What we need to do, we have to generate a file. So what we're going to do is we're going to tell the operating system, hey, wait a minute. Standard output stream by default is the display, the monitor. But when you run the executable, don't use the default output stream of the display. Instead, make a file called test.html the output stream, so that whatever we write into the output stream gets written into that file. And you'll see here that test.html is not in here. And but we will see it appear in just a moment. I have to hit enter twice there. There it is, test.html. And let's look at that inside Notepad. There's the HTML. So that's the procedure. So for those of you who are not working in Visual Studio or Xcode, you'll need to have a command line prompt like this and run the code like that. But if you're in Visual Studio, you have an alternative, and that is you can go into Properties here, into Debugging, and for the command arguments, you can redirect standard output to a file like that. Let's see if that works. It's test.html. So I'm going to delete the old one. And let's run this. But you know what? I'm going to let me get rid of this. We don't need these. We don't need these. Well, didn't show up here. And I think the reason is it's up a level. It's right there. So in Visual Studio, this is the debug folder is not the working directory. The working directory, when the Visual Studio launches and runs the program, is one level up from debug. It's the solution folder or the project folder. Now, what we need to do is we need to put the rest of the HTML in there. And inside here, we need to generate 100 random numbers and have those appear inside that list element. So how do we do that? Well, we're going to use the rand function. That's it. Rand, you call rand, returns a random integer. We just print it. We do that 100 times. I don't want you to do it 100 times that way, by the way. I don't want to bother going out to the file all the time, so I'm going to take off that setting. We're just going to look at it in the display. And I'll put these back in there. We only need one. There's random digits, but that doesn't work very nicely. So let's go ahead and put a new line character in there. Let's see it run now. So you've got the beginning of the solution here. So we're printing a list of random numbers. And look at the random numbers. 41, 18, 467. Okay? Let's run the program again. 41, 18, 467. That doesn't seem very random, does it? It's the same list. What's going on? It's not a true random number. It's called a pseudo random number generator. A pretend random number generator, not a real one. And a pseudo random number generator depends on what's called a seed. So we have to pass a seed into it. So we're going to set the seed. So we could set the seed like this. You have to call srand, and you put a number in there. I think the default seed is 0. Let's try that. 38. Oh no, it must be a different one. Now we're getting a different number. 38's our first number. Let's put a 1 in there. Maybe that's the default. '41. So actually, the first so it looks like when we don't seed it explicitly, it looks like a 1 is being passed in. So we could pass in any number we want here, and each time we run it, we're going to get hopefully a different sequence of pseudo random numbers. But what people normally do is they base it on the number of seconds that the current time is expressed in. And so you call this function called time, you pass in a 0, that returns the number of seconds that have elapsed since some epoch. And the typical epoch is January 1, midnight of 1970. And that's the historical reasons they do that. I don't know if that Visual Studio is doing that, but that's a typical epoch that's used. Anyway, it's a lot. It's a big number. It's a number of seconds that have elapsed since some epoch. So let's go ahead and we have to include C time, by the way, because this function, its definition is in this this section of the C++ library, standard library called C time. So we need to include that. And now, without changing the code, every time we run it, we'll get a different value. That's 10,751, 10,771. So we're getting a different value. 10,787. They look pretty close, though, don't they? They're all in the 10,000s. Still getting 10,000 in there. Okay, so but I don't want you to do this. You know, you can copy something over 100 times, but that's not how I want you to solve the problem. And I actually may put that in the web page there. I want a loop. Actually, I do think I say a loop in there. So I asked for a loop. But I want you to use a loop. I'm going to add text in there to require a loop. So when you read through chapter 3, you'll see it talking about different kinds of loops. And one type of loop is called a for loop. That's ideal for this situation because a for loop is used when we know, typically when we know exactly how many times you need to iterate. So the form of that loop looks like this. For int I equals 0, I is less than 100 plus I. So now we have a loop, and you can see we indenting this line. This expression here says do whatever is in between the opening and closing brace. In this case we have one statement in there, but we could have any number of statements. Do whatever appears within the opening and closing brace until the loop condition there becomes false. So we're going to execute that statement in there until I is no longer less than 100. And every time we execute the statements inside the body of the loop, they call that the body of the loop. Every time we execute those statements, at the very end, we increment I. That's what that expression does. And this expression here, there's three expressions in there, and they're separated by semicolons. The first expression is an initialization. This is as execution first arrives at the loop, before we execute any statements inside the body of the loop, the initial code is executed. So I is declared. It's initialized to 0. That's done once before anything else is done. And once that's done, then the system evaluates the loop condition. Is I less than 100? Well, we just initialized I to 0. So yeah, 0 is less than 100. So that's true. That means go ahead, execute the body of the loop. So execute the body of the loop. And when we're done executing the body of the loop, we do this third expression that's in the for statement. We increment I. Now I is no longer 0. Now I is 1. Now what do we do next? Well, we compare I to 100. Well, 1 is still less than 100. Let's execute the loop. Again, we keep doing that, printing this, calculating the random value, generating the random value, printing it, incrementing I. When I hits 100, then this expression, the loop condition, becomes false. And we stop executing the body of the loop, and we continue execution down there. That's it. So for those who are in lab, we'll take up from there. You need to do these exercises in lab. So we'll see you on Wednesday or later today.